So, let me first discuss assignment 4 with you. As I had promised, I will try to give you problems which depict all possible cases that can occur when you are solving the primal dual algorithm, when you are using the primal dual algorithm, and you may have to use an artificial constraint to obtain a starting feasible solution, a starting feasible dual feasible solution. So, problem 1 is straightforward application of the dual simplex algorithm. So, you can see that the cost coefficients are all non-negative, but the starting dual solution made up of a slack and a surplus variable will be primal infeasible, right. And so, you will have dual feasibility, and therefore, you can proceed with the dual simplex algorithm. So, problem 2, I am saying that you obtain a basic solution with x1, x2, x4 as the basic variables. So, that means you will start your basis consisting of columns A1, A2 and A4, and show that it is neither primal nor dual feasible. So, by pivoting you will reduce this set of columns A1, A2, A4 to identity column, do the operations, all the elementary operations, and then what you get at the right hand side will not be all non-negative. So, it will be it will not be primal feasible, and also your Cj minus Zj's, the relative prices will also not be all non-negative. So, this basis is neither primal feasible nor dual feasible. You have to use the artificial constraint technique to obtain a dual feasible solution and proceed with the dual simplex algorithm. Okay. You should finally be able to show that the primal is infeasible, which means that you will be concluding that the dual is unbounded. So, when you are proceeding with the dual simplex algorithm, remember what the condition is for detecting that the dual problem is unbounded, which will imply in turn that the primal is infeasible. So, you should be able to show that. Okay. Now, let us go to problem 3. Problem 3, I am saying that the tableau below shows a basic solution which is neither primal nor dual feasible again, and you are applying the artificial constraint technique to obtain a dual feasible solution. Apply dual simplex algorithm and obtain an optimal solution which is not dependent on M. So, I am trying to acquaint you with the different situations that are possible. So, the solution is not dependent on M, which means that the artificial variable that you attach to the artificial constraint is not is present in the basis, right. Therefore, the artificial constraint is not tight. So, your objective function value will be not dependent on M, and so you can make the usual conclusions, right. Okay. So, when you obtain the final tableau, you will see that your okay. Then we go to problem 4. So, the simplex tableau below shows a basic solution which is neither primal nor dual feasible. Apply the artificial constraint technique to obtain a dual feasible solution, then apply the dual simplex algorithm, and note that the artificial constraint is binding. That means, your corresponding artificial variable is at 0 level in the optimal solution, and the objective function value depends on M. This would imply that the objective function is going to minus infinity as M goes to infinity. Yes, because remember, your solution that you have obtained is optimal. So, therefore, the coefficient of M in the objective function will be negative, and so as M goes to infinity, the objective function value will go to minus infinity. This implies that the primal problem is unbounded. If the primal is unbounded, you will conclude that the dual is infeasible. So, I am asking which dual, because you applied the artificial constraint technique to obtain a dual feasible solution. So, I want you to think about it as to what is happening here, because one way you are concluding that the primal is unbounded, but that means the primal, which primal is unbounded and which dual is infeasible. So, please just make sure that you know what is happening. Okay, I would like you to. So, this problem is an exercise through that. Okay, so this is the table, and you are supposed to do it. And I am saying that x1, x2, x3 can be chosen as the starting basic variables, but the solution is not feasible, primal feasible, right? But it is well, it is neither. Yes. So, you can start with x1, x2, x3 as the basic variables. So, you have a basis here, but you will have to add the artificial constraint to obtain a dual feasible solution, right. In problem 5, I am saying that the application of the primal dual algorithm to the shortest path problem show that for I belonging to W, remember I had defined the set W as the collection of nodes from which T is reachable, and the moment that happens you put the node index in the set W. So, the corresponding dual variable value pi I is the length of the shortest path from node I to node T. This you should be able to prove using the fact that why I got included in W, and therefore, using the fact that the corresponding dual constraints, some set of dual constraints are binding or are satisfied as equality, and from there you should be able to show that the corresponding dual variable pi I for I in W represents the length of the shortest path from that node to T. Okay. Then problem 6 is again an exercise. In the primal dual algorithm, we have seen that the value of the dual objective function value increases by a positive amount. Yes, because your when you continue with the primal dual algorithm, the restricted primal value objective function value is positive. That is why you continue, you modify the dual solution, because as long as the restricted primal objective function value is positive, you do not have a feasible solution for the original problem. So, then you modify your dual, and that means that your objective function value for the dual is increasing by a positive amount at each iteration. So, this should imply that the algorithm will terminate in a finite number of steps, but when should that happen? So, if not, then explain. So, I am asking you to sit down and just work it out. It should not be difficult. You should be able to figure out why, even though the objective function value for the dual is increasing at each iteration, and dual is a maximization problem, you cannot guarantee that the algorithm will terminate in a finite number of steps. So, you either be making some conclusions and then saying that of course, you will terminate in a finite number of steps, but why? So, I want you to explain that, right. Okay. So, this is assignment 4, and I will continue with my parametric and the sensitivity analysis in the lecture. So, let me just get back to the calculations for the 19th lecture, and I had used the revised simplex algorithm. Let me just write out we were doing the change in right hand side vector. So, we were discussing this sensitivity analysis, and I had used the revised simplex version of the dual simplex algorithm. So, what was happening is that we wanted to remove variable which became negative, because you increase the value of lambda. So, a particular variable, basic variable became negative. So, we had to remove it from the basis, and to do that I needed to. So, if I am computing, if I am using the dual simplex algorithm, then I need the top row and the row corresponding to the outgoing variable. Now, in the revised simplex, you simply carry the extended basis inverse. So, that means you have to compute the top row and the second row, because here the second basic variable was going out of the basis. So, you need to compute both the rows to take the ratios for determining the incoming variable. Okay. And so, this is what we did. So, therefore, to compute the 0th row, you need to multiply CB B inverse, which is available to you in the extended inverse. You need to pre-multiply CB B inverse with each non-basic AJ, right? And that will give you your, so you will get the, so CB inverse with, so you will do it with AJ, and then you will compute and then compute CJ minus CB B inverse AJ. Okay. So, once you get this quantity, you subtract it from CJ, and that will give you the top row. To compute the second row of the tableau, you need to pre-multiply the second row of B inverse, which is again available to you. You need to pre-multiply the second row with each aj corresponding to the non-basic variable with each aj, right. So, once you have the second row and the top row, then you can take the ratios and determine the incoming variable. And now, let us continue. So, we have considered the changes or the small sensitivity analysis of the right hand side values of the cost prices, and now and then we also I think we worked out adding a new food if it is available and so on. So, now let us see if you add a constraint. The idea is that adding a constraint. So, adding a new constraint. So, it is possible that the ministry or whoever the controlling authority is might decide that you need to have another nutrient in the you must have a restriction on the another nutrient, and maybe what you the controllers may specify a minimum quantity or a maximum or equality, whatever the situation. So, if you add a new constraint of the kind summation a m plus 1 j x j, j varying from 1 to n, let us say less than, greater than or equal to b m plus 1. Okay. So, whichever the depending on the nutrient, if they do not want it in excess or whatever it is, but it is possible, right. So, then if you have a new constraint, so you can convert it to equality. In case it is not equality, then it can be rewritten, can be written out rewritten as an equality constraint, because you want equality constraint, right. So, saying that summation a m plus 1 j x j, j varying from 1 to n, let me say it is a slack variable, it is less kind. So, you are saying x n plus 1 is equal to b m plus 1. Yeah, now let us point out something here before I do this. At this point, what you will do is that you have an optimal solution. If it satisfies this constraint, then we can conclude that the current solution is optimal. And why? Because you see, if with the added constraint, let f1 denote the new feasible set, f1 denote the new feasible set, right. So, then f1 is a subset of f, because you have added one more constraint, right. Initial feasible region, if it was this, now you have added another constraint, or whichever way. So, the region becomes smaller. So, definitely it may be either the same or it may be contained in f, right. So, this implies what? This implies that the minimum of C transpose x over x belonging to f1 will be greater than or equal to minimum of C transpose x subject to x belonging to f. So, in case your current solution is feasible for the new problem, it is in f1, then it means that you cannot do better than what you already have, right, because here the minimum may be bigger. If the original optimal solution did not belong to f1. So, in case it does, then you have the best, but if you do not have, then you immediately see that you will have a case for. So, that means your constraint, whichever kind, will not be satisfied by the current optimal solution, but optimality criteria does not get disturbed by adding a constraint. So, you have a situation made for tailor made for the dual simplex algorithm, right. So, then we can start with the dual simplex algorithm, and this is where I want to show you, because yes. So, you will add a slack or a surplus variable, like I have added this, but the value here for x n plus 1 for the current optimal solution will not be a non-negative one, it will be negative because the current solution is not feasible. So, then you can start with your dual simplex algorithm. So, let me work out an example and show you the yes. So, suppose calorie content. So, a new policy stipulates that the calorie content of the diet should not exceed 2000 calories. Okay, so that means the constraint is of the less kind. So, which means that, and of course, you have to know what are the calorie contents of the 6 foods that you are considering. So, yes, let me just have the data here. Okay, so it says that, so therefore, this says that 160 x 1 plus 20 x 2 plus 450 x 3. So, these are the numbers which are the calorie contents per unit of the different foods. 250, 450 this plus 250 x 4 plus 300 x 5 plus 360 x 6 should be less than or equal to 2000. Yes. And your current primal solution, optimal solution, current optimal solution is given as 0, 0, 0, 0, 11 by 2 and 7 by 4, right. And you can just verify from here that this would be 150 into 11, which would be 150 into 11 would be this, and then this would be 7 by 4. So, 90 times 7 is 630, right. So, this is 0, 8, 2, this, which is greater than 2000. So, the current optimal solution does not satisfy your new constraint. So, we need to start from where we are, because so I can use this thing, and the optimality condition is satisfied by this basic feasible solution. So, I can start my dual simplex algorithm. Now, I can add a slack variable here to write it in the equality form, and therefore, the constraint becomes 160 x 1, or maybe I should say that adding a slack variable x 7, the constraint reduces to 160 x 1 plus 20 x 2 plus 450 x 3 plus 250 x 4 plus 300 x 5 plus 360 x 6 plus x 7 is equal to 2000. And we see that since the right hand side up to this point the value is 2280. So, therefore, this implies that your x 7 is currently minus 280, which is less than 0. So, therefore, the current basis is no longer feasible when you have added this constraint, and so I need to find a different new basis so that I get a feasible solution and hopefully optimal, otherwise I will have to work for it. So, essentially, so the idea is that we will apply dual simplex algorithm, but since I have added a constraint, my basis size has gone up, right. And so, what I am saying is that in general, if you add a constraint, then these are the numbers corresponding to the, so I am again assuming that the first m variables are basic variables. So, when you write out the new basis, the extended basis, this is the slack variable you have added, and therefore, these are the coefficients in the added constraint. So, this is the expanded basis, and I need the inverse of this, and again by simple matrix methods you can see that the inverse of that expanded matrix would be. So, I can obtain it once I have the basis inverse for this. I can obtain it by, see, this is already there, then here it will become minus a m plus 1 comma 1. So, the same vector multiplied by B inverse, and this you can check for yourself that this is the inverse of this. Okay. So, once you have the new basis inverse, we can then proceed with the dual simplex algorithm, and of course, I have in the last example I showed you how to do the revised simplex algorithm version of the dual simplex algorithm, right. So, we will have to do the same thing, and now if you go back to this example that we have been discussing. So, here this was my basis inverse, this is your minus CVB inverse. So, you have added, since x5 and x6 were your basic variables, so 300 and 360. So, this is what you add here, and then this is B inverse, and so essentially this is your new basis inverse. This was 3 by 3, and this is your right hand side, right. So, this is the final revised simplex inverse or the tableau for the current problem with the added constraint, right. And so, we will have to remove x7 from the basis, right. So, apply, that means apply dual simplex algorithm, to obtain a feasible basis, right, a feasible basis, and hence an optimal basis, because the optimality criteria will not be disturbed, and I have already discussed with you. So, what you will do is, in order to continue with the dual simplex algorithm, you will need to compute the third row, because you now have the basis inverse, and you will need to compute the top row, you have the CVB inverse, and then once you have the top row and the third row, you can take the ratios and see that and then decide on the incoming variable, and continue with the dual simplex algorithm. Okay. So, what we have seen is that here definitely because you do not have the whole tableau, when you want to proceed with the dual simplex algorithm or maybe other versions of the simplex algorithm, you need to generate the data. That means, you need to generate the top row, and you need to generate the row corresponding to the outgoing variable. But see, the thing is that you still are not using as much space. Your storage requirement is very, very low. You are only making the necessary computations, what you need to proceed with the algorithm, and you are not carrying the whole tableau, because you do not need, if you have 1500 variables and you just need one to come into the basis, then why should you do calculations for the remaining 1499 or whatever the variable. It depends on the this thing also, the number of constraints. But anyway, so there is a definite saving in your computations when you use the revised simplex version. And so, I have tried to show you this, but of course, for small problems you can, when you want to do things by hand, you may carry the whole tableau, and it will be much quicker for you to see to decide on the incoming variable and so on. So, as I said, so now all programming is done for the revised simplex version, because the whole tableau is never converted at every iteration, only the necessary computations are made. So, I hope you have now obtained some feeling for the sensitivity analysis that we do after we have obtained the optimal solution. Now, changes in the other part is changes in the input output. See, then two names for input output coefficients. The coefficient outputs Aij, right. So, these are the elements of the matrix. We call them input output coefficients. We can also call them technological coefficients because they reflect the technology. See, for example, in the diet problem, when you say that this is the amount of fat available in the first food, that means that whatever methodology you have of extracting the how you prepare the diet will depend. So, your content of the fat that you get from the first food will depend on the how you prepare the diet, right. Sometimes the fat may get burnt and so on if you overcook or whatever it is. So, these coefficients are often called as the technology coefficients or the input output coefficients. So, we want to also look at how you can study the changes in the if you have if the input output, that means you may have a better technology of preparing the diet. In that case, these numbers may change. So, can you make use of calculations that you have done so far in trying to take care of the changes in the input output coefficients. Okay. So, let us see, and then okay, let us first just look at the So, again two cases. One, suppose Aij goes to Aij plus let us say delta Ij, where Aj is not a basic column. Okay. So, it is not a basic column. Therefore, what will change here? In case Aj is not a basic column, the only change that will occur would be in the relative price, that means in the Zj. So, this implies that your Cj minus Zj, so bar will be equal to Cj minus, and this is Cb B inverse. I can write Aj because only this entry has changed. So, Aj plus Ei into delta Ij, right. Only the ith entry in the jth column has changed. So, this is Ei times delta Ij. So, when you rewrite, this will be Cj minus Cb B inverse is your Zj, Cb B inverse Aj, and here it will be minus Cb B inverse Ei times delta Ij. So, that means this is the ith coefficient of element of Cb B inverse, which is nothing but the ith dual variable, right. So, this will be Cj minus Zj minus Cb B. Oh, okay, why should I write that? I want to say that this is equal to Yi star into delta Ij, where Yi star is the optimal dual variable. Okay. And so, you want this to be greater than or equal to 0. If you want to find out for what values of delta Ij would your current solution remain optimal. So, then this would imply that see, I want to get this. So, this is greater than or equal to 0, and certainly if so delta Ij, I am taking the situation, it depends. Okay, delta Yi star may be negative or positive. So, this implies that your delta Ij is less than or equal to Cj minus Zj divided by Yi star if Yi star is greater than 0, right, or it is greater than or equal less than here in this case, because this comes to this side and you divide by Yi star. So, this is this, otherwise it is greater than or equal to Cj minus Zj divided by Yi star if Yi star is less than 0. Because if I have the standard formulation, then there is no restriction on the sign of the dual variables. Otherwise, for the canonical thing, that means if for minimization you will have less. So, the Y star would be the non-negative. So, depending on whatever the situation, right. So, I immediately have this thing that if delta Ij has to be less, if delta Ij becomes more than this, then the corresponding Cj minus Zj will become negative, and so you will now have feasibility, but won't have optimality. So, we can continue with the, in either case, if your Dij exceeds the required limit. So, as long as Dij in this case is less than, or in this case greater than, then your current solution remains optimal. You do not have to do anything, but if it exceeds these limits, then you can proceed with the simplex algorithm. Right. Now, in case the Cij changes for the basic variable Aij, then you have to do more work, and let us see how we take care of it, and then I show you through an example. So, change in Aij when Aj is in the optimal basis. Okay. So, we want to look at how to take care of this. See, the thing is that that means in this case your Aj will go to Aj plus delta Ij Ei, and let me call this as Aj prime. So, we actually want to see at this point, once you know what the you have already obtained an optimal solution, and then you realize that no, your Aj should have been Aj prime, then it will require a few more iterations, because I cannot trace back my calculations. So, the idea here is, but we will use the current solution, and which would mean that, see, what I do not want Aj column Aj anymore, right. So, that means what we will say is that let us treat the corresponding variable xj as an artificial variable. Right now, it is in the basis. I want to drive it out, and one way we learnt the technique, maybe probably I did not discuss. I did mention it as the big M method, but we will talk about it now. So, the idea here is want to remove Aj from the basis, right. It should not figure in any optimal solution, because Aj is no longer a feasible column for me. So, therefore, we will use the big M method. So, what we will do is keep Aj in the basis right now, with cost as M, a very large positive number, right. Because if M is a very large positive number, since we are minimizing the cost, Aj, if it is possible to obtain a feasible solution without Aj, then this will help us, because M is very large. So, an optimal solution xj should not figure, provided I have a feasible solution from among the other variables, right. So, a very large positive number, and this is what we call as a big M method, right, and keep Aj prime as a new column. So, that means you have added a new activity as a new column or activity, as they call it. In this case, in our case, it is a new food, as a new column with cost price, with cost Cj. So, this is our legitimate column now, and this is not legitimate. We want to drive it out of the basis. So, what that's therefore, one more column will get added, and yes, now the idea is that, and so you will proceed with the simplex algorithm, but before that, so because Aj is currently in the basis and you have changed this objective function cost, you have changed the cost Cj to M, and remember when we were discussing the price ranging for a basic variable, you have to recompute. So, here recompute the CBB inverse with changed cost of the basic variable basic variable xj. Because the cost has changed, so I will compute this and therefore recompute this, and also the Cj minus Zj for all the variables, including xj prime, right. Xj prime corresponds to your aj prime. So, you will do this and then you will start with the simplex algorithm, because you want to drive out. So, obviously, once because you have taken m as a very large number, there will be at least one legitimate variable whose relative price would be negative, and so it will be a candidate for entering the basis, and we continue with the simplex algorithm. Okay. Now, I did not discuss this. This is known as the big M method. When you do not want a particular variable in the, but you need it as a device, because in this case I have a ready-made tableau, I have a basis inverse, everything corresponding to aj being in the basis, right. So, therefore, it helps to start the computations from there. Therefore, currently aj is in the basis, but I want to drive it out. So, then the idea is that you can give it a very big price, so that it is not profitable to keep it in the optimal basis. So, as the process of the simplex algorithm, it will go out of the basis if you have a regular this thing from there, right. So, let me work out a problem, and then I will discuss what can be the possible implications of adding giving a very big price to a variable when you do not want it in the basis, right. Okay. So, let me give you the data here. This is suppose a richer version of food 3 is available. So, what I am saying is that suppose this is when suppose a richer version of food 3 is available, which means what, that in the market with protein content. So, with protein content as 3 plus alpha, originally it was 3 with 3 plus alpha at a price 50 plus alpha rupees. Okay. It depends. So, now you want to know food 3 is not part of your basic feasible solution, optimal basic feasible solution. So, you want to know when would this food become competitive, when would it become a candidate for being included in your optimal diet, right. So, obvious question would be to find out what the Cj minus Zj would be. So, therefore, let us find out. So, the C3 minus Z3, the new this thing would be 55 plus alpha minus, remember our dual solution was 3 comma 8, and this thing would be your the protein content is the second one. So, the first yeah, I have to go back to the this thing. So, yes, we were computing this richer version is there. So, the new this thing would be as 55 plus alpha minus okay, this would be food 3 with fat content 3 plus alpha. So, this would be, there is a plus alpha here. Yes, so this is 3 plus alpha. Okay. So, this will come out to be 6 minus 24 minus 8 alpha. So, the whole thing comes out to be, this is 30. So, 25 minus 7 alpha, we want this to be greater than 0, which implies that your alpha is less than or equal to 25 by 7. And this, remember the formula I gave you that had the yi star here, but here it is not yi star, it would have been yi star 8, but since the price also changed and I did not take that in my calculations when I was discussing the change in the aij corresponding to a non-basic column, I did not take the change in the price, I kept the price as it is. So, with the change in the price, the number becomes 7 here, and this. So, if alpha is less than or equal to 25/7, then it says that the food would not be competitive enough to be included in the optimal diet. You can the current solution is optimal even with this new data, with the change data. But in case alpha is greater than 25/7, then C3 minus Z3 will become negative, and you can proceed with your simplex algorithm to enter A3 into the basis and stop when you get the optimal solution. So, this is the calculation for a change in Aij corresponding to a non-basic column. Now, suppose change in Aij when Aj is in the optimal basis. So, X food 6 is included in your optimal diet, and let me give you this. So, that and the fat content. So, suppose fat content for food 6 goes up to 2 plus alpha, and the cost reduces to 22 minus alpha rupees. Okay. So, the fat content has gone up, and therefore, the food the price has come down. Right. Now, you want to again find the range for alpha such that the current solution remains optimal. Current solution remains optimal. Okay. So, we will need to find out because the price also has changed. The price has changed for a basic food. So, I need to recompute the So, what we were saying is that we will so your A6 will currently, so that means this has gone up to 2 plus alpha and the cost reduces to this. So, what are we doing now? We are adding your column A6. Your column A6 therefore has gone to, originally your column A6 was column A6 was 2 2. So, A6 was 2 2. Now, your A6 prime has become 2 and 2 plus alpha and this, because the fat contents refers to the first. So, this is 2 plus alpha, and A6 is in the basis right now, A6 prime is not. So, we will keep A6 prime in our tableau wherever we have stored the original data. So, that will be there. A6 is 2 2, but now we say that change C price of X6 is M now. Price of X6 is M. Okay. So, which means that your CBB inverse has become, because X6 is the second one, and what is your price for this thing? For the first one, yes, X5. So, this is 27 and this will be M, right, and this will be B inverse. So, this will be your new CBB inverse, which means that this will be 27 M, and yes, so B inverse is minus 1 by 2, 1 by 2, 3 by 4 minus 1 by 4, right. And so, that turns out to be, which I have shown you the computations here. So, these are the computations. So, your new CBB inverse will be this, right, and therefore, the new objective function cost would be this without the minus, and then this is your current basic feasible solution with A6 as the activity column. So, this is it, right. Then it turns, so we will start with the simplex algorithm, because I want to make use of the calculations that I have. So, therefore, yes, with this new CBB inverse, I need not write it here, it is already shown in the table, that is why. So, now you start with your C1 minus Z1, new this thing, right, and it turns out that the C1 minus Z1 is equal to 174 minus 3m upon 4, which is less than 0, because m we are taking to be a very large number. So, the moment m has a negative sign, no matter what number here is, what we say is that m is sufficiently large. So, that means that this is less than 0. So, this implies that A1 is a candidate for the optimal for the new basis. Okay. And I have already done the calculations here. So, this would be the your y1, this column is y1, and this is your C1 minus Z1. Okay. So, we will pivot on this. Just want to show you the calculations a little bit. So, pivoting would mean what? See here, yes, you want to you have to decide on the pivoting element. So, since this is negative, this is your pivot element, right? This is your pivot element, and so you want to make 0 and 1, 0, 0 and 1 here, and which means that the second that means now your A6 will go out of the column, right? Because currently A6 was the second column in your optimal basis, current optimal basis. So, pivoting on this one means that A6 will go out. So, therefore, you would have and what would that mean? That if A6 is going out, that means it is no longer in the basis. To check whether your calculations are right or not, these m's should disappear from your calculations, because they would not be because your CB will not be a function of m. Therefore, CBB inverse would not have any component of m, and so your new top row should be independent of m. And I will quickly show you how, because you see this number you can write 174, you can write this 3 by 4 times, this is 58, 3 5s, and yeah, 58 minus m, because this is 3 by 4 already. So, that means this row I multiply by 58 minus m and subtract, fine. If I multiply it by 58 minus m and subtract, I will get this number. So, just do that. So, here this is 54 minus 3m by 4 minus, you have 3 by 4, 58 minus m. So, you see minus 3m plus 3m, it will cancel out. Okay. So, without wanting to do, I just want to show you that here plus minus 3m plus 3m. So, this number m will go out from here, and similarly, if you look at this one, you are multiplying this row by 58 minus m. So, then minus 54 plus m upon 4, and this will be plus 1, because you are subtracting 1 by 4 times 58 minus m. Okay. So, here again m by 4 and minus m by 4, this will go out. So, once the CBB inverse, that means your calculations are okay, because the new CBB inverse is independent of m, and then here also the new objective function will be there when you make a 0 here, and then one can continue with the calculations here. So, your new basis is x5, x1, and depending on the sign of then we will again start computing your new C2 minus Z2 and C3 minus Z3, and if I satisfy the optimality criteria, then this is my optimal solution. Otherwise, I will continue with the simplex algorithm till I reach till I satisfy the optimality criteria. So, one can this sort of takes care of most of the changes here. You might say that we have not thoroughly discussed this technique of adding making the cost coefficient of a variable very large. So, what are the possibilities? Because since we do not want that particular variable, in this case, you see, if I do not come to a situation where this vector is going out of the basis. That means if it continues to be in the basis, then I do not have a feasible solution with a new column, because this continues to be in the basis. So, what I will do is that maybe after I have discussed the parametric part also, we will come back and visit the big M method, and I will try to discuss the theoretical aspects of that. Okay, so, we will do that later on. So, the next topic in the post optimality analysis would be parametric analysis. Okay. And let me just introduce you to the topic, and then we can work out the details in the next lecture. So, the other part is, and the reasons are very obvious why we want to include this also, parametric analysis. See, okay, so consider a situation. See, we have a linear programming problem, minimize z equal to C transpose x, subject to let us say again, let me consider the canonical case, and x greater than or equal to 0. So, the diet problem, or maybe some other situation where there is a manufacturer and he is producing some items, and these are the raw materials available. Okay, in that case you would prefer, fine. So, consider equality, that means say the product mix problem. So, you have the raw materials available to you are given here, and then you want to produce something, and you are minimizing or maximizing, does not matter, but this is a situation. What happens is that some of these items, not all, maybe some, are under government's control. That means they will not be freely available. So, in that case, there may be a policy that in batches the raw materials, some of the raw materials may be released by the government, and this may happen at the last moment. So, therefore, this becomes parametric in the sense that this controls the amount which is available to you in the market. See, the government, depending on again the situation, how things are available, how the production is, there must be some places where these items are being produced, and you want to make sure that, so the government will have a control and will decide to release certain items in the market from time to time. But as a manufacturer, you have to be sure that you are prepared, because this may happen at the last moment, but you have to set up your production levels much before, and you have to plan. So, therefore, you may want to know, okay, what would be your production levels depending on the value of theta. And again, this linear simplex algorithm allows you to really do this kind of parametric analysis. So, we will call it this is known as the parametric right hand side problem. Okay, so this makes a lot of sense. And then if you look at its dual of this problem is maximize this equal psi equal to b plus theta b prime transpose y subject to A transpose y less than or equal to C y unrestricted. Okay. So, because we also the primal and the dual are so well interconnected, it makes sense to also look at the parametric version of the cost function, right. So, therefore, if this is parametric for the right hand side, the dual will become parametric. So, this would be known as parametric cost vector. And I did the sensitivity part first, because sensitivity part allowed you to only change one Cij or one Aij or one Bi at a time. Now, here what is happening is that more than one Bis will be changing according to the B prime, right. and so theta is the parameter. So, B prime is given to us, it is theta. So, again there is only one parameter, but the thing is that your right hand side vector may change by more than one component. So, this is the idea. And so, we will now try to look at this, and again through examples I will try to acquaint you with the methodology and so on, and we will not make it very rigorous, but I will try to just work out examples so that you can, at the first this thing you can understand what is happening.